Okay, today I'm going to lecture on multivariate stats and principal components analysis. So what does multivariate data look like? Um, in general, we're talking about um, tabular data for the purposes of this class, where each row is a particular instance or object or record, and each of the columns is a variable associated with that particular object. So in this case, this is a land cover data set that the USDA collects, and each individual object is a unique pair of location and year. So for instance, we have the observations for Alaska in 1949, Alaska in 1954, etc. And the variables shown in that little window on the left are the fraction of land in various types of land cover. So grassland or range, rural transport, rural parks, etc. Now, when we have multiple variables, if we want to graph them, one thing we can do is a matrix of scatter plots, where each scatter plot looks at two variables at a time. So you've probably seen these matrices of scatter plots before, and they're very good for allowing us to look at pairs of variables, and maybe in some cases we can actually develop some preliminary relationships among three or more variables, particularly if we have three variables that are all highly correlated with each other. Then we might be able to look at an image like this and say, okay, well, these three variables are all highly correlated with each other. That's great, but it's difficult to try to get at where you might have, say, more than one pattern of variability going on. And we can't really assess redundancy very well. That is, unless all the variables are highly correlated with each other, it's hard to tell whether there are more than one pattern of correlations in the data just from looking at a matrix of scatter plots. It's possible to actually put more than two or three dimensions onto a particular graph. This is an interesting graph. This is from a data set of the dimensions of parts of irises. And here we're showing three dimensions spatially: sepal length, sepal width, and petal length. And there are two more pieces of information being shown. One is species, which is shown by the coloring, and then there's another dimensional variable that's being shown by the size of the particular the spheres, where each sphere is identifying a particular object or instance of the data. So how do we describe variables in a multivariate data set? Well, some of the things we're interested in are the same things as we'd be interested in with univariate data. That is, for each variable, we're interested in the univariate mean, x bar, and the univariate variance, s squared. And those are indicators of the central tendency and dispersion of the particular variable. And when we have multiple variables, the thing that comes in addition is association. How does each variable relate to the remaining variables? And how are variables simultaneously related to multiple other variables? Are they positively or negatively related? Or are they unrelated? So the measure of association we're going to look at first is covariance. So the covariance of two variables, x and y, is the summation along all of the observations we have of the residual of x and mean x. So x sub I, the ith observation of x, minus x bar, the mean x. The product of the residual of the x observation and the mean x, and the y observation and the mean y. Okay, so sum that all up for all observations I from 1 to n, and divide by n minus 1. So if you look at the equation, what you should be able to recognize is that when for an individual observation, x is greater than the mean value and y is greater than the mean y value, right? Those two residuals are going to both be positive. And so they're going to have a positive contribution to covariance. Alternatively, if those residuals are both negative, so that particular x is less than the mean x, but y is also less than the mean y, then you're going to have, again, because you're multiplying two negative values, a positive contribution to covariance. So covariance is going to go up whenever you have pairs of observations that are both above or below the mean value for their respective variables. Alternatively, every time you have an instance or when the x variable is greater, say, than x bar, but y is less than x bar, you're going to have a positive and then a negative value, and their product is going to be negative. So the covariance is going to be lower. And of course, the same is true in the opposite case if x is less than the mean and y is greater than the mean. So, and then of course, if you actually look at covariance between x and y, but you look at the same variable twice, so you're actually doing like the covariance between x and x, what you can see is that the covariance equation reduces to the variance equation. Okay, that is, it reduces to, say, xi minus the mean x squared, because x and y are the same. And we'll see that the covariance between a variable and itself is going to be equal to the variance. So if we just look at a particular collection of data points for two variables, in case one, if when variable j is greater than the mean, when that's true, variable k is also greater than the mean, and vice versa, that when variable j is less than the mean, variable k is also less than the mean, most points are going to add a positive value to the covariance. So you're going to have a positive covariance. On the other hand, when variable j is greater than its mean, variable k tends to be less than its mean, most points are going to add a negative value, and you're going to get a negative covariance. Finally, when you have a balance of points where there's, where j is greater than mean, but k can be, 50-50, less than or greater, and vice versa, you're going to wind up with, a low or zero value for covariance. So a covariance matrix for p variables is a matrix or an array of whose dimensions are p by p, and it displays the covariances between the pairs of variables. So, for instance, the value in the jth row and the kth column gives the covariance between variables xj and xk. And the covariance matrix is symmetric, so the value in the kth row and the jth column is also the correlation between variables xj and xk. Along the diagonal of this matrix, we're going to have the covariance between each variable and itself. And as I said before, that reduces to the variance of the variable itself, with the covariances in the off-diagonal elements of the matrix. The correlation coefficient is an alternate measure of association. So the population correlation is defined to be equal to the covariance between two variables divided by the product of the standard deviations of each variable taken separately. So we see that in the upper right. The R, which we use for correlation coefficient between variables j and k, is equal to the large hand S, that's covariance between j and k, and then the variance of j times the variance of k. Okay, so if there's a perfect positive relationship between variable j and variable k, then the covariance between the two is going to be equal to the product of their standard deviations. And so that correlation coefficient will be 1. So at the bottom, I'm showing you just sort of a graphic display of what various values of R actually look like. At the left, an R of 0. It's basically just a scattershot of points. There's no relationship between them. And R of 0.7, that shows there's a pretty high relationship between the two. And then an R of 0.9 shows an even closer relationship between the two variables. Now, when the correlation coefficient is raised to the second power, okay, we call that the coefficient of determination, or R square. And when we do that, when we square that R value, we interpret that value as that one variable explains a certain fraction of variance in the two variables that is common to both. Okay, so you might say in the middle that's an R of 0.7, and we would say that there's 49% of the variance in the two variables are common to each variable, or 49% of the variance in one is explained by the variance in the other. Finally, note that lowercase r is used for correlation coefficients between two variables. Uppercase r is used as the correlation coefficient between one variable and an estimate derived from multiple variables. And then similarly, with p variables, you can have a correlation matrix that's a p times p matrix that displays the correlations between the pairs of variables. In this case, what you will find along the axis, the diagonal, will be values of 1. So the correlation of any variable with itself is 1. Quick note before we get into principal components analysis, principal versus principal. As a noun, principal refers to one who holds a presiding position of rank, or capital or property before interest. And as an adjective, it means the first or most important in rank. So the head of a primary school or secondary school is a principal because they are the first or most important in rank. Principle is a noun, and in its primary sense, it refers to a basic truth or law, assumption, or rule. It's always principal, the rank related one that we are referring to when we refer to principal components analysis. So, what is principal components analysis? A statistical procedure that uses orthogonal transformation. Orthogonal means at right angles in multidimensional space to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. Principal components is going to be used to condense the information contained in a large number of variables into a smaller set of new composite variables that explain almost as much variance as the original variables. So, motivation for principal components analysis, as we said, when you have a large number of variables, a scatter plot matrix may be too large to study or interpret properly. So there'd be too many pairwise correlations between the variables to consider, and graphical display of data may not be a particular help if the data set is very large. So if you have 12 variables, for instance, there will be more than 200 three-dimensional scatter plots to be studied. When you take 12 variables 3 at a time, you need more than 200 three-dimensional scatter plots to look at every possible combination. To interpret the data in a more meaningful form, it's necessary and highly useful to reduce the number of variables to a few interpretable linear combinations of the data. And each linear combination will correspond to what we call a principal component. PCA, by the way, can be considered a special case of factor analysis. It's another term you might hear. Factor analysis is actually more general because it can have both orthogonal and non-orthogonal axes. That is, the axes, as we'll see for factor analysis. In PCA, they have to be at right angles. In factor analysis, they don't. So here's just showing a mess of scatter plots that one would have to look at for a particular data set that I've used before. And you can see the patterns just become very difficult to try to suss out. So when we have correlations between X variables, and we call this multicollinearity in the context of regression, the data may more or less fall on a line or a plane in a lower number of dimensions. So, for instance, a plot of two X variables may have a nearly perfect correlation. The graph on the left there has a good correlation. It's not perfect. And those data points fall close to a straight line, okay? So rather than describing those two variables separately, we could just, well, number one, we could just use one of the two variables and understand that that other variable is covariant, but we might not want to pay attention to it. Or we might say, well, maybe there are two effects here, but one effect explains most of the variability in both variables. And so we might, if we draw a line through sort of a imaginary ellipse fit to the data, and here I'm labeling it PCA1, that index is going to represent the overall trend in both variables. And if we draw a line orthogonal to it, at a right angle to it, label that, say, PCA2, that will give us sort of either the error that is associated with any individual observation, or it might give you a second effect that's going on in the data separate from the main effect. Here the main effect is that pressure in a closed system is going to increase as temperature increases. Going to higher dimensions, suppose we have a test and we test a verbal, math, and logic exercises, and we get 3 different scores, 1 for each. So we have 3 variables, but the variables may be highly correlated. And so it might be, I don't think it would be in real life, but it might be that we really only have 2 dimensions of data, and that's what's being plotted here. We have X, Y, Z, and those could be verbal, math, and logic. But when you actually plot out the data, you see, oh, actually, most of the points fall in a particular plane that I've shown there, plane, a 2-dimensional figure, with, some slight variability displayed, as sort of the height of that plane, okay? And so even though we have 3 variables there, we've really only got sort of 2 dimensions of variability. And very often you'll hear PCA discussed as performing a reduction in dimensions. That is, if you extrapolate to many more variables, you can imagine that a large number of variables might similarly be explained by a smaller number of dimensions. Note that if you actually give perfectly or very nearly perfectly correlated variables to PCA software, it very often gives you an error that refers to a singularity or a singular matrix. In that case, you have to remove a variable or possibly more than one variable in order to get rid of those perfect correlations. This can also happen when 2 or more variables sum to another. So for instance, with those land fractions that we looked at earlier, those would, for any individual observation, sum to 1. And in that case, you will likely get a singular matrix. And so you've got to drop out one of the variables. So here is generally the steps involved in doing a principal components analysis. So starting there on the left, imagine we have some data points. I haven't put in the data points in those images, those graphs, but you can sort of imagine that there are data points that are contained within, or maybe 95% of them are contained within that ellipse, okay, that's being shown. And you can see an example of that at the lower right. There's 2 variables and sort of fitting an ellipse such that 95% of the observations are contained within the ellipse. So you just have to imagine that for the graphs at the top. So we start with 2 variables, x1 and x2 in this case, and we have 2 means, mu1 and mu2. Mu1, the little 1 is not there. I don't know why. So we start there. The first thing we do is we subtract the mean values from x1 and x2. So this has the effect of moving the origin of the graph to the center of mass of the 2 variables, so the central tendency. And what we're going to do is we're going to use that point in that third part of the diagram to rotate those axes such that the first axis is aligned with the long axis of that ellipse that's fit to the overall, that's really the long axis of the distribution of the points. And that axis will be our principal component 1. And then, because this is in 2 dimensions, the principal component 2 is going to be at a right angle to that first axis. And this is why sometimes you hear principal components analysis referred to as an axis rotation approach. That is, you'll hear, we're going to have a new set of axes that are aligned with the variance of the patterns of variance in your data set. And I've just shown you there, if you can imagine that little red point being a point in the original data set, it had a particular set of coordinates associated with x1 and x2, and the principal components for it are going to be similarly its position, but relative to the 2 axes, principal component 1 and principal component 2. So we're going to be measuring the distance along principal component 1 as its score for the first principal component, and then it's the distance along principal component 2 from the origin, that's going to be its coordinate value for that second principal component. So that's sort of the very conceptual approach about how you're doing principal components. Of course, that's only in 2 dimensions, and we want to generalize to n dimensions. So imagine that you have a vector of variables, okay? X, so x1 is a variable, x2 is a variable, etc., etc., etc. And it has a variance covariance matrix of all those values. And consider that you could have a set of coefficients E11 through E1p. So that would be a set of coefficients, one for each of the variables in the original data set, x1, x2, etc., all the way up to xp, that would give you a new variable, y1, which will be our first principal component. And then another set of coefficients, E21 through E2p, that will give us our second principal component analysis. And I'm sorry, second principal component, and so on and so forth through p principal components. Each linear combination is a linear equation that predicts a yi, the ith principal component, from x1, x2, etc., xp. There's no intercept, but ei1 or ei2 or eip can be viewed as coefficients of an equation. And that new variable, yi, is going to have its own variance, okay? And each of the y's, pairs of the y's, will have a covariance, okay? And then we can just sort of put all those coefficients into a vector. And how do we find the coefficients that we want in order to do this rotation of the data in multiple dimensions? Well, the solution involves eigenanalysis, and it involves eigenvalues and eigenvectors that are produced by an eigenanalysis. So we're going to have a set of lambdas, lambda 1 through lambda p, and those are the eigenvalues of the variance covariance matrix. And these are going to be the variances of our principal components. Okay, so for principal component 1 through principal component P, we're going to have a variance associated with each one, and the eigenvalues that come out of the eigenanalysis are going to be equal to those variances. And the nice thing is that the first eigenvalue is going to be the largest one, and the pth eigenvalue is going to be the smallest one, and they're all going to be ordered such that from the largest to the smallest eigenvalue, or largest to smallest variance. So the most variance will be explained by principal component 1. The second largest amount of variance is going to be explained by principal component 2, etc., until the least variance will be the pth eigenvalue. And then we're going to have vectors E1 through EP, and these are known as the eigenvectors. Okay, so the eigenvectors are the full set of coefficients required to take the original variables and turn them into these principal components that have the property that the most variance in the data set, the most correlated set of relationships, will be summarized in the first principal component. Okay. Now, the way we actually come up with these coefficients is through the use of something called the spectral decomposition theorem. We're not going to go into that, thank goodness. We're more concerned with the properties of each one of the principal components. So the first principal component is the linear combination of x variables that has maximum variance among all linear combinations, so it accounts for as much variation in the data as possible. Specifically, we're going to define a set of coefficients for that component in such a way that the variance is maximized, subject to the constraint that the sum of the squared coefficients is equal to 1. And that's just required so that a unique answer can be obtained. Second principal component is the linear combination of x variables that accounts for as much of the remaining variance as possible, with the constraint that the correlation between the first and the second component is 0. Okay, so we're going to maximize the variance of this new component, subject to the constraint that the sums of the squared coefficients add up to 1, and the additional constraint that these two components will be uncorrelated with each other. Okay, and then all subsequent principal components have the same property. They're linear combinations, they account for as much of the remaining variance as possible, and they are not correlated with the other principal components. And this brings up an important point in terms of understanding principal components and understanding their interpretation. That is, each principal component can only be understood in the context of the ones that come before it. So for instance, the first principal component is going to show you the strongest pattern of variability in the entire data set. And the second principal component is going to have to be interpreted in the context of having already taken out that first principal component. In essence, it's kind of an analysis of the residuals after you've taken out the first and any subsequent effects if you're dealing with the third, fourth, or higher order principal components. Let's look at an analysis. This is a sociological analysis. Boyer and Sabagyu looked at 329 communities according to 9 criteria: their climate and terrain, the healthcare and the environment, transportation, the arts, economics, housing, crime, education, and recreation. So note that within the data set, except for housing and crime, higher scores are better. So for instance, the better the climate, the higher the score. For housing and crime, lower scores are better. That is, you'd prefer to have lower housing costs and you'd prefer to have less crime. So this is an important thing when you're interpreting PCA is you need to look at what an increase in a particular variable actually means, whether that's a good thing or a bad thing, or it all depends in the context of that variable, right? The data for many of these variables is strongly skewed to the right, and so a log transformation was used to normalize the data before they did the principal components. So the first thing you can do is look at the eigenvalues, and the eigenvalues are going to tell you how much variance is associated with each component. So here we have eigenvalues, and they start at 0.3775. That's the largest for component 1, and the last one, principal component 9, we have 9 variables. We're going to start out with 9 principal components. It only explains 0.0018. That's what its variance is. The total variance associated with the data set is 0.5225. We've added up all those eigenvalues to get 0.5225, and then a very standard way to look at this is to then divide each eigenvalue by the total so that you get a fraction or a proportion of variance associated with each of the components. So here we start out that 0.3775 eigenvalue for the first component. That's 72.27 or 0.7227 of the original or of the total variance. Okay, so that's 72% of the variance is explained by one component. We've got 9 variables, but there seems to be one overall large effect that we can pull out of all the data. And this is precisely what we want principal components to do. We want it to be able to say, oh, well, actually, there's a few simple patterns here. The second principal component is associated with 0.0977, or approximately 10% of the variance. The third is associated with about 5. The fourth is associated with 4, etc., etc. The last column is actually the cumulative variance associated with each component. Okay, and we calculate this so that we can come to decisions about how many principal components we want to consider for a given data set. Now in this data set, 72% of the variance is associated with principal component 1. So that's telling us there's one big pattern, and then 10% is associated with principal component 2. And when you look at both of them, you have that 82% of variance being explained. And we need to make a decision about how many components we're actually going to include. We look at both the absolute proportion and the cumulative proportion when we do this. There's a sharp drop after the first principal component. That explains 72% of variance. The next only explains 10. And then after that, there's 5% of the variance in the next one. I'd argue for this data set that probably 2 principal components are sufficient, but it requires 3 to explain 87% of the variance, and since we there's also an argument for considering 3 principal components, because in essence we've simplified this data set so much that you might as well look at a 3rd principal component. This has really reduced things so much that adding that 3rd principal component is not going to require us to do much more analysis. So we'll consider those to be the only important principal components. But one way to make that decision is with a scree plot. And so you're basically just plotting the eigenvalue versus the component number. And what that's going to tell you here is, well, 1, clearly that's important. Component 2, that explains, more than the other components. And again, that sort of argues in favor of doing just components 1 and 2, but we included 3 too because it's not a big deal to add to interpret 3 components. We've saved 3 times, we've reduced the number of variables to analyze by a factor of 3. Now that we've looked at the eigenvalues, we're going to compute principal component scores. Okay, so we're going to use from the eigenvectors. Okay, we're going to use the first eigenvector, the one associated with the first principal component, and the eigenvectors, I haven't put them here as a table, but you would simply take each one and multiply it by its associated variable to get the new principal component. Okay, and that would be done for each observation. So for each community, you would plug in that community's values for climate, housing, health, crime, etc., and multiply it by the coefficient. Of course, programs are going to do this for you. You won't have to actually compute principal component scores by hand. You can interpret the meaning of each principal component using the eigenvectors. I prefer to use correlations. I will calculate principal components, and then I will correlate each principal component against the original variables and come up with a table like this, 3 principal components, and then the correlation between each principal component and the original variables, climate, housing, health, etc. So I have highlighted the highest magnitude correlations there in red. Okay, so could be a large value positive or large value negative. Of course, it's correlation coefficient, so it's between -1 and 1. That gives you what your definition of large in this context. For that first principal component, the most important variable for calculating principal components is actually arts. The amount of number of opportunities for interacting with the arts is associated with that first principal component, and then the second largest magnitude is associated with health. So you'll notice that on the first principal component, all the values here are positive. They need not always be positive, but basically they are giving you the overall magnitude of a particular observation. Now, in some cases, one variable will have a strong negative correlation with the other variables, and that might give you a negative coefficient, but it's important to remember that you're looking at essentially the magnitude of the observations, how large a score it has overall, is what gives you that first principal component. Okay, so the variables that contribute to the first principal component include housing, the availability of healthcare, transportation, the arts, as I said, and recreation. So this is what makes up that first principal component of a desirable community. That second principal component shows a contrast between health, which has a negative value, a negative coefficient or correlation coefficient, and recreation, positive coefficient. And when you see a contrast like that, what it's telling you is that once we've gotten rid of the overall availability of these particular aspects of housing, that there's a secondary pattern. And that pattern shows that areas where there's a lot of recreational opportunities, there tends to be less healthcare. Now, that requires you to do some interpretation, and it's probably an age question. That is, if your community has lots of younger people, then you probably have more access to recreational opportunities. Whereas, again, if you've got younger people, you probably don't have the same availability of healthcare in that area. I mean, alternatively, you can turn that around and say, well, in areas where you have a lot of elderly people, you probably have more healthcare opportunities, but those particular cities may not have invested as much in recreation. And then the third principal component is noting an association after you're done with taking out the variability with the first and the second principal component between recreation and crime. And again, that's probably a demographic factor. That is, in areas where maybe you have more young people, you have more recreational opportunities, but it's associated with a greater number of crimes. So again, going through the interpretation of the principal components, it's strongly correlated with 5 of the original variables: arts, health, transportation, housing, and recreation. It's a measure of the quality of the first 4 variables and the associated cost of housing in those areas. And it's more correlated with arts. So communities that have high values tend to have a lot of arts available in terms of theaters and orchestras, etc. Whereas communities with small values for principal component 1 would have very few of these types of opportunities. The second principal component increases with only one of the variables, decreasing health. So it's a measure of how unhealthy the location in terms of the availability of healthcare, doctors, hospitals. And again, that's associated, it's not in red here, but with an increase in recreation. And the third principal component increases with increasing crime and recreation. Places with low crime also tend to have better recreational facilities. And again, that's probably a demographic situation. Now, here's a very common way of looking at the results of a principal components analysis. So we're going to graph the values of principal component 1 against principal component 2. So each dot in this plot represents one community. So if you're looking at the red dot out by itself to the right, you'd conclude that that particular dot, that particular community had a very high value for the first principal component and would have high values for arts, health, housing, transportation, recreation. Whereas if you look at the red dot on the left of the graph, you would expect to have low values for each one of those variables. The top dot in blue has a high value for the second component. So you'd expect that this community would be lower than average for health, and that's because it's got a negative correlation with health. And conversely, if you were to look at the blue dot at the bottom, that corresponding community would probably have high values for health, again, because there's a negative correlation between health and that principal component. Now, in this example, we looked at principal components analysis applied to raw data, okay? So that is the raw values for those original variables. And if you use raw data, it's going to give more emphasis to the variables that have higher variances than those variables that have low variances. So for instance, in the same analysis, if you had Fahrenheit temperatures, they would have more influence than Celsius temperatures because the Fahrenheit temperatures for a given area tend to have larger values in magnitude of values than the Celsius temperatures. So that is probably not an effect that you want to have unless all of the values in your data set are actually temperatures, and then they could all be Fahrenheit or they could all be Celsius, but wouldn't matter as long as they're the same. So this implies that a principal component analysis should only be used with raw data if all the variables have the same units of measure, or if you want to intentionally weight variables with larger variance. So the other way of doing principal components analysis is to do it on standardized data. That is, if you standardize each variable by subtracting its mean from the variable and dividing it by the standard deviation, that's going to give you a z-score or a standardized score for each variable. And then it won't matter what the units are or how you've coded a particular variable. They're all going to count equally. Okay. Now, the variance covariance matrix of a standardized data set is equal to the correlation matrix for unstandardized data. Okay. Therefore, a principal component analysis using standardized data is equivalent to a principal component analysis using the correlation matrix. And I tell you this because software packages may either give you the option to use raw data or standardized data, but they might also say, do you want to use the covariance matrix or the correlation matrix? And they're actually, it's just two ways of asking the same question. Raw data, that would be the covariance matrix. Standardized data, that would be the correlation matrix. And you will get different results, not only in the absolute magnitudes of the eigenvalues, but in the percent of variance being explained by each principal component. And on the left, we've got the eigenvalue table for the raw analysis. And on the right, we have the standardized analysis. And you can see that less variance is explained by that first principal component in the standardized data set. And so what that suggests is that using raw values for the analysis tended to weight the variables that had absolutely larger scores and explain their variance with that first principal component, whereas the standardized data set spread the variance out among a larger number of components, showing a more complex pattern. Okay, so sort of an intermediate summary here. A primary purpose of PCA is descriptive. It's not hypothesis testing. So your decisions need to be made on what provides you with a good, concise description of the data. And that's, more based on like sort of judgment calls than it is any, cut and dried hypothesis test related decision-making process. We need to make decisions about what's an important correlation, not necessarily from a hypothesis testing perspective, but in this case, from an urban sociological perspective. And so you have to decide what's important in the context of the problem at hand. And that decision may differ from discipline to discipline. Some disciplines, like sociology and ecology, the data tend to be inherently noisy. And in this case, you would expect sort of messier interpretations, lower correlation coefficients, and that would make it more difficult to be sure about what you've done. But if you're looking at a discipline such as engineering, where everything is very precise, you might put higher demands on your analysis, and you'd want to have very high correlations before you made a statement. And PCA, very importantly, can be used to select explanatory variables for a regression. So if you have a large number of potential explanatory variables to work with and only a vague idea of what variables might be important, doing a PCA first and then selecting those variables that are highly correlated to the first few components is a good way of reducing the complexity. And it also gets rid of, as I referred to before, multi-collinearity, which can actually make the interpretation of regressions more difficult.